Hi everyone and welcome to the internet. So what we're going to be doing in today's lesson is having a look to see how temperature affects the rate of a reaction. So to start off, as always, we've got a question for you to have a go answering. Those of you with target grades up to grade 5, it's the one on the left. Those of you with target grades over a grade 5, it's the one on the right. I'll give you a couple of minutes to have a go at that. Okay, let's check those answers then. So obviously tick it if you get it right. If you don't get it right, then write those corrections in. So for those of you doing up to grade 5, two ways we can measure the volume of gas we make. The first is using an inverted measuring cylinder with a delivery tube. Obviously that's filled with water. You might have described it in more detail. The second one is we could use a gas syringe. So give yourself a mark for each of those methods. For those of you doing grade 5 and up, then the way that we would actually calculate the rate is we would use either an upturned measuring cylinder and a delivery tube to collect the gas, or we could use a gas syringe to collect the gas we produce, and then we just calculate the rate by doing 1 divided by the volume. So what we'd normally be doing is an actual experiment, but we can't do that. So I've got you a video of this random guy doing the experiment for us. So what we're going to see is how we would do this experiment of how the temperature affects the rate of reaction. So what we're going to be using is sodium thiosulfate, and we're going to be using hydrochloric acid. So those are the two flasks on his desk there. Now to start with, what we do is we measure out a volume of our sodium thiosulfate. In this case he's using 100 centimeters cubed of the sodium thiosulfate, and he's then going to use a measuring cylinder to do that for accuracy. Once he's got that, he pours it into the conical flask, and so in our conical flask we have the sodium thiosulfate. Then we're going to measure our hydrochloric acid, and we're going to be using 10 centimeters cubed of this one. So again, using a measuring cylinder to measure those volumes. Now, what we're going to do is we're going to add that to the conical flask, give it a swirl, and then place it onto that bit of paper with a cross already drawn on it. As we place it down, we push start on the stopwatch. Now this reaction is a really good one to do because you can see in the top right, you can see the black cross through the actual flask. Now as those two chemicals react, it's actually going to make a precipitate, an insoluble solid within that conical flask, and it makes it go cloudy. So you can start to see it's going a little bit cloudy and the cross is becoming harder to see. So you keep watching until the cross is no longer visible. And at the point that the cross is no longer visible, then we stop the stopwatch. Obviously, once you've got that, you record those results in your table. Now, that's obviously done at room temperature, and we can check the temperature of it with obviously our little temperature probe there, and we can see that that one is at around 22 degrees, so that is about room temperature. You plot it onto your results table, so your temperature and the time in seconds, and then what we're going to do is the exact same experiment but with different temperatures. And there's a range of ways that we can actually get those different temperatures. So the way they're going to do it in this video is by using an item called a hot plate, and that's the thing you can see on the right hand side on the desk there. If you were doing this in school, then what we'd actually use are water baths, so those big kind of blocky things that sit on the side. We set them to a specific temperature, and then we'd have our different flasks with the acid and the sodium thiosulfate sitting in those to get to that temperature before you do your experiment. So again, the process would be the same, because remember, when we carry out these experiments, we only want to change a single variable. In this case, we're only changing the temperature. So 100 centimeters cubed of sodium thiosulfate is in the conical flask, sitting on the hot plate to get up to the temperature. Then we measure our 10 centimeters cubed of our hydrochloric acid into the beaker in order to get that to the same temperature. So what we've got are two actual reactants getting up to our next desired temperature. Once they've got to the right temperature, what we can do is mix them together, place them onto that bit of paper with the cross again, and again time how long it takes for the cross to no longer be visible. Obviously notice the fact that between putting the actual temperature probe into the different chemicals at this point, he's rinsing it each time. If you don't do that, then what happens is you're going to contaminate your solution and start the reaction early. And that's obviously not a good way to get accurate results. So he's just double checking to make sure the temperatures are right. And then what we do is we mix the two chemicals together once more, place it onto the cross and start the timer. So what you actually find is that as you're watching this, it starts to go cloudy until you can see there the cross is no longer visible. So you can see it just fading and it's gone. So we stop the timer, note the time on our stopwatch again, and write it into our results table. So we then do this for each different temperature, so we have a complete set of results for the different temperatures and the time they take. Because this is one of those experiments they do like to talk about, then I'd suggest what you do is jot down this method into your books so you've got a record of how to actually do this. Now I've modified the volume slightly to the ones that we'd normally do in our classroom, and you can see I've suggested we do 10 crosses on the piece of paper as opposed to just the big one. Now that just means that we've got more crosses, which gives a slightly more accurate reading when we're actually looking for it to disappear. So I'll give you a couple of minutes to get this written down. Before we move on from the actual experiment itself, what I'd like you to do is, in your books, make a list of factors that you would need to control, so keep the same, in an investigation into how temperature affects the rate. So I'm literally going to give you about a minute and a half, any factors that we'd need to control when we're investigating temperature and rate. So here's some of the ones that I came up with when I was thinking about it. Give yourself a tick for each one of these you've got right. So the concentration of the acid, concentration of sodium thiosulfate, the volume of the acid, the volume of the sodium thiosulfate, the number of crosses on the paper, the thickness of crosses on the paper, the reaction vessel size, and the reaction vessel material. That's not to say that's all of them. I'm sure there are others. We could even go so far as to be talking about the type of writing implement that we use to draw the crosses, whether it's pen, pencil, etc. So give yourself a tick for each of those you got right. If you want to jot down any of the other ones, I'll leave this up there for about another 30 seconds. When it comes to any of these questions where they're asking you what variables or factors you need to control in an investigation, there's kind of 5 key things to consider. Temperatures, concentrations, the volumes or amounts, the surface area, and the materials. So if you get asked a question about anything to do with what factors or variables should we control in order to make this experiment produce accurate results, then think about those 5 headings and apply it to whatever context they've given you. So I'll leave this up for about 30 seconds so you can jot those few down. So what I've got on the screen for you now then is what we would write as our conclusion. So hopefully we can fill in the blanks here using a little bit of thought about particles and what happens when we heat things up. Now, what we've actually got are the keywords that you need for those gaps are all written in the red box at the bottom of your screen there. So what I want you to do is write down these sentences, filling in the blanks, using the words at the bottom to complete them. So I'm just going to give you a couple of minutes to get that done. Okay, let's check to see we've got these right. As always, tick the ones you've got right, and if you got it wrong, then obviously write the correct word in place. So I found that when we increase the temperature, the rate of reaction increased. This is because when the temperature increases, the particles have more energy. This means they move faster. They will have more frequent, successful collisions. So make sure you've got all those words written in. What we actually find is then, when we increase the temperature, hopefully we did think back to some of our earlier work and know that when things are hotter, particles gain kinetic energy. So that means they're going to be moving around much faster. The faster they move, the more likely they are to collide with one another, and it's likely to be a successful collision. Because if they're colliding at a faster speed, then they are more likely to reach the activation energy. And note that little sentence at the bottom there, get this written down as well. A collision will only lead to a reaction if the activation energy has been reached. So think back to that work we did on C3, where we were looking at activation energy and those reaction profiles. So that little bump on the reaction profile, that's the amount of energy we need to actually trigger a reaction. So for those two reactants to actually undergo a reaction, we've got to reach that activation energy. If it doesn't reach it, then they'll just collide and bounce off each other with no reaction taking place. So make sure you've got those written down. I'll just give you another 30 seconds in case you haven't. Let's have a little look to see what's actually happening. So on the screen here, this is at 20 degrees Celsius. So what we can see is A and B, so the green and the blue, those are the reactants. Now when they collide, then they change to our red, which is our product. So what we can see at 20 degrees, you can see they're moving quite slowly and they're colliding every once in a while. So what we've got here is a relatively slow rate of reaction. Now what we can see is the time at the bottom there is counting up quite nicely, and we've still got quite a number of those unreacted reactant molecules. So what we're going to do is just stop this one here and have a look and see what happens when we double the temperature. So this is at 40 degrees this time, and what we can see is the particles are moving faster, and you can see that because they're moving faster, they're more likely to collide, so we're getting more frequent collisions, and they're reaching the activation energy. So what we can see here is that with only 20 seconds, we've only got 2 of our particles left unreacted for each of our reactants. So this has taken half the time of our other one. When it comes to talking about rate of reaction then, what we can actually say is that rate is inversely proportional to the reaction time. So what we're actually looking at is a way to represent that mathematically at the bottom there. So we've got rate, and then we've got our proportional sign there, 1 divided by the reaction time. Okay, so because it's inversely proportional to the reaction time, then rate is proportional to 1 divided by the reaction time. So jot down those 2 points for me in your books. I'll leave this up for about 30 seconds more. What I'd like you to do now then is I've given you a graph on the screen. I'd like you just to sketch that graph as it is at this point in time. So put that line as it exists. Now this is a graph for the volume of gas we produce in a reaction occurring at room temperature, which is around 20ish degrees. What I want you to then do, once you've sketched that graph as it stands, is I want you to add a second line onto that same graph to show me what you would expect the line to look like if we did the exact same investigation but at 60 degrees Celsius. So the one you've got on the screen is at 20 degrees Celsius. What I want you to do is add a second line onto your graph for what we would expect to see for 60 degrees Celsius. So I'll give you a couple of minutes to get that done. Hopefully what we managed to draw was something like the red line there. Now you'll notice the fact it's steeper at the first part of the graph. So what we can see is we've got a much steeper gradient in the initial part of the graph there, because if we've obviously got a higher temperature, then as we saw in that animation, the particles have gained kinetic energy, they're moving faster, and therefore there are going to be more frequent successful collisions. So that means we're going to make more gas in a shorter period of time. But this is the important point. Do notice that the actual final height of the line does not exceed the blue line, the original one. Because if we are using the exact same amount of our reactants, we will always be able to make the exact same amount of product. You can't make more product, you're just making it in a shorter period of time. So do remember that if they ask you to do a graph like this and they've given you one already drawn, then do not go above the existing line, because your final volume of gas must be the same as the one that already exists, because we're going to make the same volume of gas just in a shorter time. So again, get that little note written down and give yourself a tick if you got it right. If not, then sketch this so you have got the correct one. I'll leave it up for another 30 seconds so you can do that. Last thing to do today then is your plenary questions. So either pick the one on the left for the up to grade 5 folks, or the one on the right for those of you working at a grade 5 or above. So I'll leave this up for about a minute. If you need longer, obviously I'll give you warning to pause the video. If you still need longer, then hit pause on the video now. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.